Hello everyone. Today we are going to talk about Toronto Bikeshare Machine Learning Project. Here are our 4 team members. We can follow this agenda to quickly go through our project. About the data, it comes from 3 parts. Toronto Bikeshare ridership data from 2017 to 2018, Toronto hourly climb data from 2017 to 2018, and GPS coordinate of bike station data. For the bikeshare data, it's about 3 million instances with 9 features, including from station to station, duration, day, and time. For climb data, it's roughly 17,000 rows with 28 features, including temperature, weather, wind speed, dew point, day, and hour. The company is a bike sharing system company located in Toronto. Now the system consists of more than 6,000 bikes and 625 stations across the city, and members keep growing. So our project is to identify the main factors that will affect customer bike usage and bike duration, and also to build a model to predict the usage and duration. In the data cleaning part, for ridership data in 2017 Q4, the file is missing station ID, whereas the station name is not standard. So we introduce a library called FuzzyWizard to do the fuzzy match in order to find the correct station ID. And for the trip duration time, we use interquartile range to remove any bias, and we also drop any records with less than 60 cents duration time because of the reality considerations. And for weather data, we drop columns with more than 50 non-values, and we fill missing data with the average of before and after non-values. After cleaning, the ridership data has about 2.7 million records.
Here we have some plots for the descriptive analysis. This is the bar chart for the usage of the top 10 popular bike stations in Toronto, grouped by the user type. Blue is for annual member, orange is for casual member. The bike usage of the annual member is far greater than the usage of the casual member. Next, the graph on the left is the average using second of the bike through the day. The blue and the pink line represent Sunday and Saturday. The rest of the line is the work days, Monday to Friday. Especially in the afternoon, the average using second in the weekend is much higher than in the work days. The graph on the right is the average using second of the bike through the year. Obviously, the bike usage duration has seasonality.
We are using random forest regression to do the usage volume prediction. There are about 1.3 million rows and 11 features after pivot to hourly usage, which is our target variable. We converted categorical variables to numeric, which increased the features to 60, and we split 20 as a testing and 80 as a training data. Here is our final model. And how do we get there? Well, we use a dummy regressor to set the baseline model. We also do a random forest with default setting to compare. Since the random forest fitting is pretty slow, so we do the hyperparameter tuning step by step. If you can see that when we reduce model complexity, our model behavior keep getting better and better. So in the end, when the RMSE become stable at 2.53, we stop, and we believe that is pretty close to the optimal model. And we use that model to predict the testing data. We got 2.52 as a RMSE, which is close to the training result. And that's about 21% improvement.
Next, we train models for bike usage duration. The range of the target variable is from 60 seconds to about 1,900 seconds, and the average is 707 seconds, which is roughly 24 minutes. For data preprocessing, we have to deal with the text variables. The weather, workday, and consumer type columns are converted to binary attributes per category. The train test split is 70% and 30%. We have about 1.9 million instances for training and 840,000 instances for testing. Similar to the random forest regressor, we use RMSE as the performance matrix and use the dummy regressor RMSE as the baseline. So the pipeline of the training goes like this. First, we standardize the data. Then we do a grid search on the best maximum depth of the tree using a threefold cross-validation. When maximum depth equals 20, the model gives us the best result, and the average RMSE is 247, definitely better than the baseline. The test set produced a RMSE of 242, which is not a big difference than the training RMSE. So we do not have the problem of overfitting here. To identify the main factors that affect duration, we use feature importance of the decision tree. The most important factors here are the location of the stations, user type, temperature, and time of day. Surprisingly, weather and visibility have relevantly small effect on use time.
After the decision tree model, we want to try other alternative regression model for comparison. We choose gradient boosting regressor. Hyperparameters are max steps, which is 20, and N estimators, which is 50. We ran cross-validation for the model, and the RMSE result we got is about 245. After we fit the model, we try to predict the result using the testing dataset. Comparing the true value and the predicted value, we got 229.63 for RMSE. This RMSE result is better than the baseline and the decision tree RMSE. Because of the time limit, there are still many improvements can be done for our models. For example, we can add more hyperparameters in the grid search to make the model more accurate. And because of the large volume, unfortunately, we cannot fit all the data to the random forest regressor. We only fit for the top 10 popular station. If we have more time, of course, we want to fit more data. And for the recommendations, the models we built for this project can be used for bike availability and distribution planning. Because of the member of Bike Share Toronto is continuing increasing every year, we recommend the company can consider raising the overage fees during the peak hours or acquire more bikes and dogs. Thank you so much for listening. Now we are willing to answer any questions.